an effort actually where in Chicago there will be a hub. They are trying to build a hub. And Urbana-Champaign, University of Urbana-Champaign, is also putting a lot of efforts there. Close by Purdue University also, has a fairly large group, that are interested in quantum computation. I have collaboration overseas as well. Uh, uh, there is a group in Australia, who that are really doing excellent job when it comes to quantum technology, based on silicon and traditional materials. It's very promising. As you know that we invited, a professor from the university, like a month or so ago. So we do have ongoing collaborations with some of these universities. We have some funded research as well. In this and related areas.
Mm-hmm. I was going to ask you if there were some like research projects or specific nanoscale devices that are being tested and or like in the early phases of implementation in, like, for example, any sort of medical field or solar cell storage, or if there are any devices that have currently implemented like some of the new technology coming out of quantum research.
Okay, all right. So, let's say energy, right? You mentioned energy. So in the area of energy, storage is important, energy storage, right? So when it comes to storage, obviously think of battery, right? Capacitor is also a storage element. Supercapacitor is also a storage element. Think of a battery, lithium-ion battery, which is used in, let's say, electric vehicles, right? So in a battery, what is very important is density, energy density. So you have to really store charge, right? And in lithium-ion battery, you can use actually graphene nanosheets, or quantum dots, to store energy. That way, the density, energy density goes up significantly. Same thing happens to supercapacitors if you integrate quantum and nanoscale technology. All right. Now remember, nanotechnology and quantum technology can be different actually. Nano devices may not exhibit important quantum features. So that is very important. Let's say, here is this, let's say there are nanoscale devices, there are many nanoscale devices that actually operate, that are governed by classical physics. For these devices, quantum mechanics or quantum features can be bad. For example, in a typical MOSFET that is used in classical gates, quantum tunneling is bad because you actually lose data for that quantum tunneling. But you think of your flash drive, in the flash drive, tunneling is needed, quantum tunneling is required to store electrons, to transfer electrons from one region to, the floating gate, what we call floating gate. So tunneling can be bad in a nanoscale device, it can be good in another nanoscale device. So the device that is based on, that is governed by quantum principle can be called a quantum device.
Okay.
But a nano device that is not really, benefiting from quantum should not be called a quantum device. It's still a classical device. For that, quantum, mechanism is really bad,
There's a lot of people like to, with AI, put AI in front of everything, and I think there's probably some misunderstanding of what quantum devices or quantum research what it actually is, and so I want to thank you for helping demystify quantum mechanics a little bit, but I wanted to ask a little bit more broadly about the future of quantum research and how what are some of the costs to it in this sort of research, and what sort of projections can we see in the industry for the implementation or for like the investment into quantum research?
Okay, yeah. So not many groups are working in quantum devices, only very few groups, in this country. Obviously, industry has to be involved, and fortunately, industry is getting involved, now that we have CHIPS Act, many industries are involved, in semiconductor research, even more universities are getting into this, so nanoscale devices have been, there actually, for long. But when it comes to quantum devices, as I said, quantum devices exploit quantum phenomena. And not too many, it's not that there are, a bunch of devices, this only, you can name, certain devices that actually make use of quantum phenomena. So we need more investment, in this domain, for sure. But in terms of, the prospect, right? Obviously, it's there is great potential, as you have asked me, about quantum computation, right? Quantum computation can be extremely good, for certain calculations, not for all calculations. What they say is like, there can be a hybridized quantum computational platform, that can benefit from both classical computation and quantum computation. So not all computations are good, can be actually faster, as you were saying, can be made faster, with quantum computation. It depends on the algorithm, how you design quantum algorithms, just like Boolean algorithm, you design for, use for classical computer design, right? For quantum computation, you also need to do quantum algorithms. So quantum algorithm is an active area of research, where, there is potential. Some groups are working on that, Quantum devices is another area, where you have to develop devices, without irregularities, with robustness, and things like this. In terms of future, right? So I can see that industries are getting more interested, as I was saying. Government is also, government funding is also important, and we see different efforts actually, many different efforts actually from NSF and from other agencies, funds are available in quantum research, even at the state level. As I was saying, there is an initiative, to do quantum research. So there is actually hope, all we need is to train the students, and that's where I see, as a professor, I see some barrier, because, you need to understand quantum mechanics, at least fundamentals of quantum mechanics is important, So we have to design courses, that are suited for engineers, that quantum mechanics for engineers, so where you will be solving differential equations, that is Schrodinger equation basically, but for realistic systems, so if you could train students, and develop, courses, I think, we can really, address this issue of workforce development, and then people getting more interested into quantum research.
I just wanted to thank you so much for taking the time to sit down and talk with me about this, and sort of help clarify some of the more technically challenging aspects of understanding quantum computing and where that is going in the future. So thank you so much for taking the time to talk with me.
You are very welcome. Thank you very much for your time.
Thank you.